So hello Internet and welcome to SyC Chile. Today we are with Clara Sousa-Silva, postdoctoral researcher at Harvard University. Clara is an astrochemist searching for alien life in the universe. So hello Clara.
Hi.
So do you want to introduce yourself a little bit more?
Sure, all that you've said is true. I am also a 51 Pegasi B fellow, and I am actually a quantum astrochemist. And the reason I'm a quantum astrochemist is because I want to one day find an alien biosphere, and I think it's the best way to do it.
Sounds like a very nice project. So what is exactly a quantum astrochemist?
So a chemist studies chemistry, and in my case, I focus on molecules. I do this using quantum tools, so that makes me a quantum chemist. I'm trying to understand the quantum behavior of molecules. I specifically am trying to study the quantum behavior of molecules to find them in space, hence the astro. So small tools to find molecules in space gives you a quantum astrochemistry.
And so how do you search for life in the universe exactly?
Well, there are many ways to search for life in the universe. So far, none of them have quite worked out. The traditional thought is to look for intelligent signals booming down from the heavens, signaling some sort of advanced technology, like the sort of technology we produce. We've been sending out radio signals and TV signals onto the galaxy for a little over 100 years, and they've been quite detailed and complex. Any alien civilization listening in knows an awful lot about our, entertainment choices.
And so, our spam emails.
Yes, and our terrible emails, our advertisement campaigns, our wars, our industry, our everything, our Twitter fights. So we have the tools to do the same to them, and we have been listening in to these sophisticated radio signals for a long time with the work from people like Jill Tata and the wider SETI community. And we should keep doing those things, but it's really hard to find those signals. And so far, we haven't found any. My hope for finding life is that we find any type of life. And looking at Earth, there's only one vaguely intelligent species, and only for a blink of an eye in astronomical times. So I don't want to point our telescopes at a planet that just doesn't have an advanced civilization, but has a bunch of, alien giraffes and kittens and mushrooms and miss it. And so the way I try to find alien life is to look for the signs that life didn't mean to create. So the gases that life produces that combine together to create a message in the atmosphere of a planet. So I try to look for atmospheres, and then I find an atmosphere, I try to look for molecules within that atmosphere that shouldn't be there unless there's life. A lot of people who are in this field are focusing on molecules like molecular oxygen, which is a great sign of life on Earth. If I was an alien astronomer and I saw our atmosphere's composition, I would be very excited. If I saw 20-something% oxygen in combination with the other trace gases in the atmosphere, like methane, on a planet like the Earth, around a star like the Sun, it's a really robust sign of life. And so we are very much looking for oxygen because we know that's a good sign. But there are ways of making oxygen that don't involve life.
Mm-hmm.
Plenty of molecular oxygen exists throughout the universe in lots of places that we feel very confident are not life-bearing. And so we call that false positives. So that is a problem that I think about all the time. How do we not miss it? So we can look for oxygen, and we should, and we are. We can look for other signs of life like methane or ammonia, carbon dioxide. These are all molecules produced by life on Earth in large quantities. But they're reasonably easy molecules to make. And so my specialty is to look for the really weird molecules that only life can produce. And my specific focus is phosphine, pH3, which is like a pyramid with 3 hydrogens and 1 phosphorus up top. So it's actually a very similar shape to the molecule to ammonia, but instead of a nitrogen on top, it's phosphorus. And that molecule, phosphine, is awful molecule. We can talk about it later, but it's a horrific, almost immoral molecule, if one can be immoral. But it is really difficult to make. And so in most circumstances where you would find a habitable place, nothing but life can make phosphine. And so that's become my particular molecule and my focus. It's what I've dedicated most of my career towards. But that's just one of many. And it has problems.
But so how do you actually detect it? Because they are so tiny, like
so
the planets that you're looking at, they are several light years away. So how do you do that?
That's where the quantum comes in. So if you have light, any type of light, like lights on me now, you can break them up with a prism, with a spectroscope, or even water, and you get a rainbow. Mm-hmm. And then that rainbow, we call that a spectrum, tells us lots of cool things. So if it was just the simplest form of light, you would imagine this continuous rainbow with all the infinite colors and even the invisible colors. But if that light goes through any gas, even gas we can't see, even very little gas, with the molecules we definitely can't see, then the light that comes out of the other end is modified. There's bits of it missing because the gas, the molecules within the gas have absorbed some of the colors of those rainbows. And every molecule is unique. It has its own fingerprint. It has its specific colors that only that molecule absorbs. And so we can look at light that went through some gas we can't see and go, oh, that shade of blue is missing? Must be methane, because only methane absorbs that shade of blue. And phosphine, like every other molecule, has a unique spectral fingerprint. And so if we see light that has gone through a gas, and that gas has phosphine, we can know that has happened without having seen the gas or the phosphine or anything at all. So that shade of blue that only methane can absorb, that's just one of the things methane can do. And every molecule doesn't just absorb one color. In the case of phosphine, I spent my whole PhD trying to figure out exactly what would that fingerprint be. But that meant calculating, I think, 16.8 billion transitions between 17.5 million energy levels. And that's just phosphine, a molecule with 4 atoms. And it gets much more complicated the bigger you get. And that is really hard to do. So I calculated first all these energy levels. And that is done by basically solving some really nasty Schrodinger equations and using some very large computers to diagonalize huge matrices. And once you manage to diagonalize these giant matrices using these very powerful computers, then you get this beautiful network of all the energy levels a molecule can occupy. And I often visualize them as these globes with lots of nodes. And then transitions would connect between these nodes. And the likelihood of a molecule going from one energy state to another energy state, that defines how strong that transition will be. So it takes at least a few years per molecule.
How bad is phosphine? You said it was a terrible molecule. Why did you say that?
I mean, it's bad. You don't want it near you, but I think there's probably some in you right now. There's some in most intestines. So when I first started working on phosphine, very little was actually known about it. It was either not known by anyone because it's not a molecule that's often present in the world. And the few people who knew about it because its reputation is for just being a very effective killer. So it's used as a pesticide and fumigant. It was used as a chemical warfare agent in the First World War, and then most recently by ISIS. It's really good at killing in really imaginative and quite macabre ways, all of which have to do with its interference with oxygen metabolism. It smells awful. It's reported as smelling like garlicky, fishy death. I saw a technical report that referred to it as smelling like the rancid diapers of the spawn of Satan.
Wow.
So it's bad. And it was known for being this horrific thing, and it's produced on purpose in labs with a lot of work for these nefarious reasons. It is also produced as an unfortunate byproduct of methamphetamine production. So, meth, war, death. Those are the things phosphine is used for on Earth. And so, as you can tell, it's pretty bad. It's just an awful molecule. For life that we find pleasant.
So why are you looking for this molecule if it's such a disaster?
Well, I think it has to do with this notion of what life do you look for? One of the problems of astrobiology and looking for alien life is the human bias, the fact that the only life we know is that we have on Earth. And we should try to avoid that bias. It's just quite hard to do. But I think one of the things we can start by doing is looking for life that isn't necessarily the most pleasant to us. Oxygen is lovely and, love it. Use it all the time, every day. But it is a very specific form of life that likes oxygen. And even on Earth, there are many hidden in the shadows, many life forms, interesting, complicated ecosystems that don't rely on oxygen. And because they are not reliant on oxygen metabolism, phosphine is perfectly safe. There's a certain sense that things are awful or not based on, who's experiencing them. And when it comes to biosignatures and the search for life, I think that's very much a truth we should hold high. And so phosphine, yes, it's an awful sign for life that we love, but it's a lovely sign of life, but life that we avoid. And I'm sure they avoid us too. Those organisms would die in an oxygen-rich environment, but they're cool with phosphine. Phosphine is just something they produce as they go about their business. And an oxygen-rich planet is not a likely thing for us to find. And so it is quite probable that if we find life elsewhere, it's not going to be in an environment that looks like the Earth. So I thought, maybe we look for the sort of molecules that are produced by life in non-oxygen-rich environments. And there, phosphine would be great. So that's when I started really investigating the possibility of using phosphine to find alien life, just alien life that wouldn't want to hang out with us, and we wouldn't hang out with them, and that's fine. We don't need to hang out.
And so you've been looking for this molecule in planets around other stars, light years away from us.
Yeah, that was silly. I mean, it wasn't silly. It was a good idea at the time. I was just looking for phosphine anywhere. Now I try to think with near future telescopes like the James Webb, JWST. With JWST, trying to see, okay, what planets in our galactic neighborhood could have atmospheres that are oxygen poor and could have life happily producing phosphine. Could we detect them? And I found that we could in some circumstances, super Earths, hydrogen-rich atmospheres, carbon dioxide-rich atmospheres, if they were producing phosphine as happily or close to as happily as life on Earth produces phosphine when it's allowed to produce phosphine, so when it's away from oxygen. But yes, I was looking very, very far away. It didn't even cross my mind to look in the solar system, to be honest.
And so we all know what happened next.
What happened next was that I was very silly in not looking at the solar system. But fortunately, there's a big world out there with resourceful people who did look for phosphine in the solar system, specifically Jane Greaves from Cardiff and the rest of our now very international team, who looked at Venus. Why not? I don't think anyone was expecting to find phosphine in the clouds of Venus, and maybe we haven't, but it looks like we might have found phosphine in the clouds of Venus, and that was Jane now years ago, and there was a preliminary result there, a signal from JCMT, James Clerk Maxwell Telescope, that suggested maybe that there was a signal from the clouds of Venus that could be associated with phosphine. That's when Jane reached out to me to say, okay, I know this is weird, but how weird is it? And as a phosphine expert, I had to tell her it's extremely weird. And that was the beginning of our now many-year-long collaboration.
So before we come to that, what do we know about Venus?
Not as much as we should. There was a lot of interest on Venus in the 60s and even the 70s and the 80s. But I suspect that there's only so many probes that you can melt before you decide that maybe to leave it alone and go to Mars instead, where it's not the most habitable place, but at least it doesn't melt all your equipment. So in that way, Mars is much nicer. So we kind of gave up on Venus. We had a lot of the near emissions from the Russian program that told us quite a bit about the atmosphere, and with the Mariner missions to figure out the atmospheric pressure and the general environment, the true radius of the planet. So we know enough to know it's bad.
It's not a place you would go for a vacation.
No, you wouldn't even want to, just drop a package and leave. Venus is bad. It's extremely hot on the surface, extremely high pressures, many, many times the pressure that you find on Earth. So the surface is completely uninhabitable. And as an astrobiologist, of course, I try not to be biased by, Earth life. But even without the bias of Earth life, very little complexity could exist at the surface of Venus, even subsurface. So very little hope of there being any life there. It's bad. And as you move up in the clouds, it's still pretty bad. A lot of sulfuric acid, no water, both things that we usually don't like when we're thinking of life. But the pressure is quite nice, and the temperature is quite nice. Very similar to, a reasonable summer day in the clouds, if it wasn't for all the acid. But yes, mostly it's awful.
Go back to the detection of phosphine. You say it was made by GCMT, and then you used the ALMA radio telescope, right?
Yes, and so it was many months apart. So by the time Jane had reached out to me, the JCMT observation had already happened, and it didn't have that, tantalizing indication of something that could be phosphine. But we're talking about work at the very edge of instrument capabilities. And so for something as extraordinary as finding a biosignature I had claimed was without false positives, we definitely needed a second observation. So that's where ALMA comes in. Extremely powerful array, and it was indeed a much better observation. And it seemed to, again, confirm a reasonably strong signal where pretty much only phosphine absorbs in the clouds, suggesting parts per billion abundance. And to put that in perspective, on Earth, phosphine exists at parts per trillion to parts per quadrillion. Even though it's produced by anaerobic life in large quantities, it reacts to the atmosphere very quickly, and we don't have that much anaerobic life, freely producing phosphine. But above environments where phosphine is produced, you can get quite a lot. And overall on Earth, parts per trillion, parts per quadrillion. And here we are looking at Venus in the clouds, and we have parts per billion, which may seem very little, but that's a lot for a molecule as strange as phosphine.
So did you think about possible non-biological processes that could have created phosphine? And how did you rule them out?
So that was really tough, and it's a really difficult part of any project like this, because you're basically proving a negative. You're just thinking, all right, could this make phosphine? No. Okay, next one. But how do you know when you've run out of ways to not make phosphine? It becomes this infinite task. We had a major advantage because we had done this for my paper about hypothetical exoplanets that are oxygen poor, where phosphine is being produced. What are the false positives in these hypothetical terrestrial planets? So we had tried everything already, lightning, meteoritic delivery, volcanism, tectonic plate shearing, photochemistry. We tried everything we could think of to make phosphine on these terrestrial planets, and sometimes we could make some, lightning the right way, or meteors with the right composition crashing in the right way. We could make some phosphine, but just tiny, tiny amounts, never any detectable amounts. And so I think my original claim was any detectable amounts of phosphine on a rocky planet can only be associated with life. Phosphine is just an extremely difficult molecule to make. That phosphorus and the hydrogen do not want to be together, even if you have hydrogen, which you don't have a lot of on Venus. And that's the main problem with a lot of these false positive scenarios. Phosphine exists not happily, but reasonably comfortably on Jupiter and Saturn. And there we know very much that there is no life. But we do know there's a lot of hydrogen pressure. And without hydrogen pressure, it's just really, really, really difficult to make phosphine. unless you have life.
And is it possible that you have another gas in the atmosphere of Venus that has the exact same signature as phosphine?
So, in kind of theoretical terms, every molecule is completely unique, and only that exact frequency of light will be absorbed by that molecule. But in practical terms, in the real world, molecules can be easily mimicked by others. For example, this transition of phosphine that we think we detected in the clouds of Venus, that's just one of those 16.8 billion transitions I had calculated. We only found one of those 16.8. So of course we wanted to find more of these 16.8 billion to confirm it was definitely phosphine. It's extremely hard to do it. The Earth's atmosphere blocks most of the regions where phosphine is active. And then there are other molecules nearby. And with anything other than infinite resolutions, many molecules can absorb very near each other. So there's one other molecule that could be responsible for the signal, and that's SO2. Mm-hmm. Now, it would be strange to find SO2 in the quantities we would need it to be in that region, but we're in the realm of it's all strange. And so, what's stranger, this molecule being in the wrong place in the wrong quantity, or Venusians? Obviously, Venusians is stranger, so we considered SO2 really seriously, and we decided that it wasn't a good candidate, but other people have since decided that it was actually a perfectly fine candidate. So there's still very much a discussion around if the signal is real, which molecule is causing it. We had many reasons to dismiss SO2, but I think one of the most compelling ones is we had observations across a wavelength range. Sadly, not a wavelength range where there are other phosphine transitions, but it is a wavelength range where there are other SO2 transitions. And we didn't find any SO2 there, where we knew it should be absorbing if it was present. And that was one of the main reasons for dismissing SO2 as the culprit. But there are complicated mechanisms with which SO2 could show up there and not there. It's just very difficult. And that's why we chose phosphine as a primary candidate for the signal.
So what are the main criticisms that you had to face? Can you answer to them?
Of course. So the first criticism is that the signal isn't real. Mm-hmm. Being at the edge of instrument capabilities means we are getting a lot of noisy, delicate data that's really difficult to process. And so there are ways of processing the data in which the signal disappears, and there's ways of processing the data in which the signal is there. And it's really hard to know which one is right. And people get very animated about this. The data processing part of my team does not include me beyond the very last stage. I provide spectroscopic properties for phosphine. But I think the simplest explanation of what is happening, and this is something I've discussed with several of my other colleagues on this team, like Sucrit Ranjan and Paul Rimmer, and they're very good at considering the philosophy of it all. And they made the very good point of this really boils down, whether the signal is real or not, to a difference between hypothesis testing and hypothesis generation. So the scientific method has relied on hypothesis testing for centuries, and it's a really good way of doing science. You think, I wonder if this is happening, let's test this theory. In this case, I wonder if there's phosphine in the clouds of Venus, let's test this theory. And when you use this approach and you clean the noise, it seems like the signal is indeed real, and it does correspond to phosphine. Mm. But there is a more conservative approach to doing science, and that's hypothesis generation. You take some data and you go, I'm not trying to find anything. I'm just looking at the data and seeing what it tells me. That's much more conservative, much safer. And if you use this approach, there are many ways in which you don't get a signal, and it's not phosphine. But the problem with this approach is that you can throw out when you're trying to clean out the noise, you can throw out the signal if the signal is weak. You throw out the phosphine with a bathwater in the proverbial expression. And so it's very easy to lose a signal. But in the hypothesis testing approach, it's very easy to introduce a spurious signal. So I think the current debate, the very healthy debate around whether the signal is real or not, comes down to this. Are you testing a theory, a hypothesis, or are you generating hypotheses? But let's say the signal is real. That takes us to the next criticism, which is maybe it's not phosphine. We discussed this a little. It can be SO2, and that would be strange. It's just not as strange as aliens. So that is something we're still figuring out. We do know SO2 exists on Venus, though why would it not be seen in the wider bandwidth? So that's still a point of discussion. And now there's many teams that are critical of the discovery, but think the signal is real, but it's not phosphine. Or think the signal is real and it's phosphine, and that takes us to the third layer of criticism, which is, if it is real, if it is phosphine, is it life? And that, as you said, if we could confirm it, that would be one of the biggest things we have ever done as a species, find buddies elsewhere. But it's almost impossible to prove. Proving that the signal is real and that it is phosphine is very much within our reach. It's within my reach even, that's how within someone's reach it is. But proving that it's life means proving that it's not everything else. And that list is near infinite. So I don't think it can be done based on the detection of phosphine. It has to be done by detecting every other molecule that this potential ecosystem is producing. So we can paint a holistic picture of this biosphere and really understand what's going on. It won't just be one life form producing one biosignature and that be phosphine. It will be a complex network.
So what would life look like in the atmosphere of Venus?
Well, I mean, that's very speculative.
Yeah.
So make sure when you're editing this, you don't go, well, it's this beautiful alien. I mean, I think about the Venusians a lot. If they're there, we don't know, but we know they must remain in the clouds for the duration of their lives. They can't ever go to the surface and, take a break. They have to fly or glide or float for their entire lives. And so it has to be a purely aerial biosphere. So in my mind, I imagine, Venusian manta rays in the clouds. But the most likely thing, if there's life in the clouds of Venus, and that's a very large if, but if there is life in the clouds of Venus, it will probably be very, very simple, microorganisms that have managed to spend their whole life cycles in the clouds, moving just from different layers of the clouds that allow them to multiply and get food and energy in a safe way. But I think it's likely to still be a pretty tough life. If it's a biochemistry, anything like ours, they're going to have to be shielding themselves from the acid. Even the most capable extremophiles on Earth that can handle a lot of acidity, they can't handle those lives. And even the most competent extremophiles that can handle very little water, they can't handle the dryness of the clouds of Venus. So if it is a biochemistry like ours, it's a miserable existence, and my heart goes out to them. They would have witnessed a mass extinction across many, many, many generations as the planet became less and less uninhabitable. So if I had to design a space mission going to Venus, I would design it to not go in. I am, I think, different from a lot of people who think if it's aliens, we definitely should go and scoop it up and look at them, sniff them, find out what they like and don't like and how to kill them. I think because there's a small chance it is life, we should be extremely careful. And I think we should not go until we know exactly how to go safely and ethically. I often think that if there's an alien civilization that we have not detected that's watching us and is watching us now do this great astronomical leap into potentially interacting with our first alien species, and the thought that we could do it and then massacre them by mistake, just by our presence, just by our interference, or that we could go and contaminate the environment so we'll never really know what they were like before us. I think that would be a really embarrassing thing to do on the galactic level. I think it would be a really serious planetary offense, and I don't want to risk that. If it is life, I want to watch it from afar until I know enough to know that I can reach without hurting them. So I think if I could design a mission, it would be a very powerful observatory orbiting Venus, mapping its incredible clouds, its weird lightning, its composition, its convection currents, the strange effects that we still don't understand, like the mysterious UV absorber. I want to know everything about it remotely, and then figure out how to make a safe mission that can observe whatever is happening in the clouds of Venus as respectfully as possible. So I actually think if it is life, we shouldn't go there.
What would be the implications of finding life elsewhere in the universe?
I actually think these fall into two categories, right? There's finding life next door or in our solar system, and finding life out there. As we talked about before, I didn't really think there was any life in the solar system, so I wasn't looking. And I was hoping that life was, to some extent, inevitable, given the right circumstances. A lot of astrobiologists believe that life is inevitable, considering the right circumstances. So I thought this too. And I was hoping these circumstances were sufficiently common that we actually could find this life. And that's still my hope. But if we find life in the solar system, in places that we already know are pretty weird, they are not like places we find on Earth. If we find life in the clouds of Venus, or signs of life coming out of the plumes of Enceladus, or near the oceans in Titan, these are not places that have an analog on Earth. So if life can originate in these places and on Earth, then life must be literally everywhere in the universe. And so it means that life is not just inevitable, as I expected, and not just common, as I had hoped, but so common and so ubiquitous throughout the galaxy that we live in a busy, busy place with just life in every solar system that we can find, and there are 300 billion of them in our galaxy alone. And so suddenly I just feel like we would not be special at all, but we would be so comforted by all the life that exists everywhere. And I think people really like to think Earth is special, but I think they would give up that idea if they would feel a lot less lonely. And I think that's exactly what would happen if there's life in the solar system. It means there's life everywhere, and we are not special, but we have galactic buddies everywhere.
Thank you so much, Clara.
You're so welcome.